Welcome back to Machine Learning class. In today's session, we're going to apply the neural network model to one example. In this example, we're trying to use the model to classify or recognize the handwritten digits. Again, we're going to follow the six-step pattern of using the scikit-learn for machine learning model purposes. The first step, as we know, is to understand the data, then load data into the computer memory. The second step is we need to split data into train and test. And for the X variables or the features, we also need to standardize them. Thirdly, we need to create one scikit-learn model instance because the whole scikit-learn model is built on the class concept. We need to create one instance of the particular model class at choice. The fourth step is we need to train the model using the trained data as input. After that is done, is fifth step, which we're going to predict using the testing data with the model that has just been trained. The last step is we want to evaluate the model's performance. So if you have watched the previous videos or in the class, you should already know the six steps pattern we've been using for the scikit-learn machine learning model. Today, just one more chance, we apply the pattern to the problem that we want to solve. First step, we need to understand the data, then load data into computer memory. The data to us is not unfamiliar because we have used this data for several times. We first used the data for the logistic regression example case. And then we also asked some students to use the same set of data for the KNN presentation. Again, here's a summary of the data. We can download the data from external source, a website. Basically, the data set is a collection of handwritten digit images. There are 70,000 images in total. Each image is one handwritten digit. Because the image is made of 28 by 28 pixels, it is grayscaled image, means has a value, each pixel has a value between 0 and 255. The value represent the darkness of pixel on the image. Here, just one example and what the image look like. And you can tell clearly, in this case, is digit number 9 on the screen. Let's also look at a few more examples in the digit sample set. So now the data has been randomly selected, then sorted in a way that is the first row or all the digits have been labeled as 0, and the second, all the digits have been labeled as 1, then labeled as 2 and 3, and so on and so forth. For most of them, we know it's pretty trivial effort. We can easily tell what the digit is based on the image on the screen, but some of them could be a little bit more tricky or ambiguous. I just circle some of those for your own test, because when we look at those, even probably for humans, we're not so certain what really that image is for. Just there's some kind of ambiguity out there. Probably different people will give the different answer when we look at the same image. Anyway, this is kind of a data we're dealing with. So we are kind of finishing the first part, understanding part of the data. Now what do? We're going to write some Python code to load the data into computer memory. The code itself has comments. The inline encode comments are self-explanatory. Let me just talk through quickly. Here we're defining the data path where the source data, the image data is located. And Now this block will give us the choice. Um, the choice is really between whether we already have the data in this specified location or not. If it is not there yet, what we are going to do is we go to the website, we'll submit a request, and then download the data and put it under this particular path where we want to store the data. After that is done, we need to load the data into the computer memory from the file. The file itself is actually MATLAB file format. This particular Python function will load the MATLAB file at this particular location into the computer memory. Lastly, we'll clean up data a little bit and make the final data into a Python dictionary with 4 keys. The first one, data, is really the features, the X variables in the data for all the observations. The target is the Y variables of all the observations in the data. Then their description and calling names as additional 2 keys in the dictionary. So if you are kind of uncertain with what the dictionary means, please go back to session 2 and 3 of this class, in which we reviewed the Python data structure and defined the variables types, including the dictionary. All right, after this step, all the data is loaded into computer memory from the file. Now, the second step, what we need to do is split data into train and test, then standardize the features. This step literally completes the data splitting. We are making 1/7 of the data going to testing and the remaining of data going to training. And when we do the split, we also know this represents the X variable, and this for the training, and this X variable for the test, and the Y variable for the training, and the Y variable for the test. And the data will be split in that way. After that, we need to standardize the features. This is pretty much a requirement for all the machine learning methods, which relies on gradient descent approach. We talked about the rationales why doing that in the past. Anyway, let me just tell you the scalar come with scikit-learn package. This scalar is doing the standardization. What that means is, if you think about each individual X variable, X1, X2, X3, in our case, we have 784 features because the image is 28 by 28, so each image has totally 784 pixels. Each pixel is one feature. So each pixel can potentially have a value between 0 up to 255. If you look at the pixel by pixel, do the mean or do the standard deviation for each pixel, it could be quite different from pixel 1 versus pixel 2, pixel 3. So the job for standardization is doing some kind of rescaling transformation. After that, all the pixels, no matter it's the first pixel, second pixel, across all the training data, will have a mean at 0 and a standard deviation of 1. Again, this is a very standard procedure for data pre-processing before we calling a machine learning algorithm, which is based on the gradient descent approach. This will just help make the training, the gradient descent approximation and approaching to the optimal more efficient. All right, after step 2, we're going through steps 3 and 6, 3 to 6. And the step 3, as we see here, we are declaring and is creating one instance of particular machine learning model. In this case, we want to create um, a neural network classifier, and that's the name you should call. And there's some like more parameters in this classifier associated with scikit-learn's implementation. I'm going to keep this to a later part of this lecture. And let's just assume those are the good settings for all the parameters we want to use for this particular machine learning a neural net classifier. Okay, and then step 4 is pretty trivial. We just fit in the training X variable and training Y variable into the model class we have just created. So this step will do the job of training the model. After that, step 5, we're going to predict using the model that had just been trained on the testing data. And step 6, we are going to do a model performance evaluation of the predictions for the testing data. And we're looking at the two metrics, accuracy rate and the confusion matrix. And for step 4, 5, 6, 7, or 4, 5, 6, and also the accuracy rate and confusion matrix, for now, the students should be already familiar with, because we have talked those several times in our logistic regression session and in our k nearest neighbor sessions. So you should already know those by now. You may also notice that I purposely have printouts for the timestamp. This just helps me to see if on each step how long does it take to execute. With that, we actually are able to get the training, the prediction, and assessment evaluation of the model's performance. And with this particular model, with the particular setting we're having on the previous page, we are able to achieve an accuracy rate of 97.37%. And on this page, we are seeing the confusion matrix from this testing set after we have trained the model. Again, just remind you, if you see the numbers on the diagonal, those are the counts of correct projections. Correct classification or projection just means the model prediction and model's labeling is consistent with the actual label in the image data sets. So everything, the counts on the diagonal line are correct classifications. Means model is doing a good job, doing the right thing, doing the right classification. But anything other than on the diagonal line is misclassification. But overall, we can see we have very good classification from this model. So next step, I'm looping back to the model creation part, which I didn't talk much in the previous page. There are several critical parameters I want to have a little bit more discussion. The first parameter is alpha, which I have 0.01 here. Alpha is the penalty term coefficient in the scikit-learn package. It is actually equivalent to the lambda coefficient we talked about in our previous session. Because in our previous session, we talked about to prevent overfitting, we want to make a penalty term based on the number of coefficients in the model as a part of the overall cost. So this part of cost is a penalty on number of coefficients for the neural net. Is really the square of all the weights in the neural network applied to certain coefficients, lambda or alpha in scikit-learn's case. So this is a penalty term, and the other part is cost. this kind of pure prediction error type of cost. As we know in classification problem, we often use cross entropy as this cost component. So anyway, the alpha itself in our class, in our case, we're setting it to 0.01. So the next setting is number of hidden layers and the number of nodes on each hidden layer. We're choosing to have two hidden layers. In the first hidden layer, we have 150 nodes, and on the second hidden layer, we also have 150 nodes. With a neural net model, you only need to pick hidden layers, how many hidden layers, and how many nodes, neurons in each hidden layers. So why we do not need to specify the number of nodes in the input layer or the number of nodes in the output layer? Why is that? I'll give you a couple seconds to think about it. Well, the answer is the number of nodes in the input layer and the number of nodes in the output layer is not a model structure choice. They are coming with the data itself. In our case, each image has 28 by 28 pixels, in total 784 pixels. Each pixel is corresponding value will go into each of the 784 nodes. And then on the output layers, we know this problem are the handwritten digits cases. There are only 10 potential labels, potential values for the y variables. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So totally only 10 choices. What the model does again is get the inputs pixel values as inputs to the neural net and going through all the calculations through the middle layers, hidden layers, eventually project out the probability on the 10 nodes. Each node kind of represent the label for different digits. Eventually, the model will give probability distribution across all the 10 nodes on the output layer, or probability for what the digits could be across 0, 1, 2, 3, all the way to 9. And then algorithm will later pick a max probability across all the 10 probabilities. Let's see if the max probability is 3 across all the different potential labels, then the 3 will be the final answer for this classification on particular image. If another image comes in and the maximum probability across all the 10 nodes is on see number 8, then the number 8, the digit 8 will be the model's prediction, model's classification for particular example. So the short answer is we only specify the hidden layer numbers and the nodes, and because that's kind of a choice of the model structure, and the number of inputs and the number of outputs nodes is not a modeling choice. It's kind of given by the data itself. One more thing to discuss about activation function. In this actual example, I'm using ReLU activation function. It's somehow different from the sigmoid or the logistic function, activation function I have introduced in the last two sessions. So by now you should already familiar with the sigmoid or the logistic function, which have kind of S-curve shape. So ReLU function is somehow different. It represents rectified linear unit. So what does is for anything, if the z based on certain linear combination of inputs with threshold value z is less than 1, less than 0, and the activation just returns 0 back. if the z value becomes greater than 0, then what it returns is actually identity. If the z value is 5, ReLU will return 5. If z value is 10, ReLU function will return 10. Is basically on the side above 0, the ReLU function is identity function. It's kind of linear line, 45-degree linear line. Below 0, it just returns 0 all the time. So this is how the ReLU activation function defined. Sigmoid function is very early on activation function used in the neural net. Over time, ReLU function has becoming more popular and widely used in neural nets and deep learning cases because it still gives you some kind of response at the value going up. And where for sigmoid, when the value going up, like become greater than 5, or on one hand, or less than -5, it just flatten out, means it's going to lose responsiveness, lose differentiation when the z value becomes really extreme. ReLU, at least on one end, resolve that problem. You still get response, still get differentiation when the z value going to be extremely positive. So that's the sigmoid and ReLU function, activation function. If I use the ReLU function, I'm able to retrieve an accuracy rate of 97.37%. If I switch it to sigmoid function with everything else identical, I can retrieve accuracy rate of 96.99%. If we convert into number of misclassifications, we're getting 267 out of 10,000 because we only have 10,000 images in our testing data versus 301 misclassification out of 10,000 testing images. So there's about a lift of 10% when we're switching the activation function from sigmoid to ReLU. As research goes, people also have a different activation function called leaky ReLU. So what it's trying to do is it's trying to solve the problem that is for ReLU, whenever the z value is less than 0, it just kind of flatten out, doesn't do anything. There's no differentiation anymore. Leaky ReLU on the positive side still same as ReLU, just identity function, or just like y equal to z, y equal to itself, something like that. However, on the negative side, when the is on the negative domain, it's going to slightly change the response at a certain slope, at certain coefficient a. So a, it can also be optimized or set up based on certain intuitions. Anyway, leaky ReLU is one further improvement on the top of ReLU. However, currently scikit-learn does not support leaky ReLU function yet. So in our case, we can only stay with ReLU because of lack of choice for leaky ReLU in scikit-learn. Quickly also mention a few other things in the models, parameters choice. We also have initial rate of learning. We talk about this kind of coefficient, the fraction of a fraction of a value that we want to apply to the gradient descent derivative value. Basically, a smaller value like this means we are trying to take a baby step to prevent overshooting based on the gradient descent kind of a slope. And adaptive just means once we have initial learning rate, the learning rate as the iteration numbers goes up, will be adjusted dynamically, because whenever we're getting closer to the optimal, the learning rate also need to be generally like narrowed down, because the once we getting closer to the optimal value, optimal point, the overshooting problem probably will become more likely. Anyway, this pretty much covers everything we want to talk about for using the neural net for the for the handwritten digit recognition case. All the slides, and here, and I want to just show the code, right? So the code pretty much just what I talked about in the slides. And if we click on the run button and take about 40 seconds to get everything finished from the beginning to the end. Of course, how long time it takes really depends on your own computer's hardware setup. Yeah, here is roughly what I get from my own execution of the program on my computer. And here's 97.37% accuracy rate using the ReLU, and here's a confusion matrix. They are just same as what I just showed you in the slides. Anyway, this is our last session before the winter break. And the next release of the video for the class will be after the new year. Thank you all. That's it for today.